So welcome again for the KAUST Supercomputing seminar. This is today about the chapel. And so before going into the presenting our guest speaker, so I will present an overview about KAUST Supercomputing Lab. As you see, it's a small team, but very active. And Shaheen is the name of our supercomputer, and it's Arabic name as a Peregrine Falcon. You don't name a supercomputer after like a total or small thing because or slow thing. So you want to have fast thing. And the Peregrine Falcon, as you know, when it tries to get its prey, is the fastest animal on Earth. So it can go up to 350. And KAUST has in its DNA, since its creation in September 2009, they brought a supercomputer. As you can see, in 2009, we had the fastest in the Middle East and ranked number 14, Blue Gene P at that time, with 64,000 cores. And then after 6 years, we had Shaheen 2, which is a Cray XC40, and we had close to 200,000 cores, and with a peak of 7.2 petaflop. And we had a great thing, we had over 1,200 publications, 700 projects, and almost 2/3 of the KAUST faculty using, and many of you are still here. And now for less than a year, we are in production with Shaheen 3, which is a Cray EX, and it's as of now we have only the CPU part, and we have and it's pure Genoa, as you can see over close to 40 petaflop. And soon, by the end of the year, you are all waiting, we'll have hopefully the GPUs. As you can see, we have already some early success. So some of your colleagues got the ACM Gordon Bell Award for this boosting Earth system model, where they did mixed precision and they tried to do compression of the storage. We had also HPC Wire, where we have colleagues in not only David Keys, who is well known and assisted with Hatem Al-Tayef, but also our colleagues here, Naga, who developed HPC GVCY, so which is an open source for parallel implementation for processing over 20,000 genome sequencing. And so we look forward for the next story with you. So what we are doing on Shaheen? Are we doing games or no? There are people that are doing approximately 25%. You are doing combustion, 15% climate, 13% chemistry, then geoscience, agriculture, marine science, and so on, with bioinformatics and so on. So it's pretty kind of diverse scientific workload. We have success story again, with real application, McLaren, where we have collaborated and we had papers, and we were able to detect some performance bottlenecks. We have also a success story in the excellent return of investment. This is our neighbor, the King Economic City, where they wanted to build a wall of 4 meters high. And when the people did the modeling and they tried to see how much is a wave and so on, they said that you don't need to build a wall for 4 meters. So 1.8 was more than enough, and it saved $500 million. So you see the return ROI, indirect cost. Also, you see some people I know many of you are in climate. So how we started with regional, and now even some people are doing up to a meter scale within the city. Some of you have already access to Shaheen, but some of your colleagues don't. So I'm sharing with you, it's easy. You go to the hpc.kaust.edu.sa, you talk with your PI, you write a project proposal. So once you apply, it is reviewed, and then we can give the final recommendation. Okay? And also I would like also to make sure that we have also a great collaboration with HPE, especially with Agnello. So we have what we call Shaheen 3 Advanced Collaboration Center, where we can accelerate scientific computing through advanced collaboration, not only with HPE, but also with AMD and NVIDIA. And some success stories already have been done with GWAS or distributed linear algebra, or doing efficient in situ visualization, or doing combustion theory. So if you want to learn more, please contact us, or especially Agnello Exposito, who is here with us online. And so this seminar would not be available without the support from HPE, and especially Agnello, who was very helpful in the last couple of days, where on Friday we set up everything. And again, I would like to thank Agnello, but also our guest speaker. So before introducing our guest speaker, so thank you all for attending online and on-site, and I see a lot of people. So it's a mix. You see people, student, postdoc, researchers, some faculty. And the great news, most of you don't know Chapel, so that's why we are here to learn. Okay, and also, what are you doing? So it seems like many of you are doing Python. Okay, this is great. But also, like I can see like Fortran. So Fortran is not dead. So there is a great thing. So C++. And also, what is your field of science? So you are doing like it's quite diverse, like from geophysics. Someone, can someone mute his? Someone. Okay. Okay. Sorry. So we are doing also DJ. So we have also like some people in matter science, geophysics, climate. So, and I think it's enough for me for talking, and I would like to introduce you a great speaker. And I have seen him many times virtually. I had the chance also to collaborate with him at various HPC events, mainly like into reviewing. He was a great like chair. I recall like his leadership at ISC. And I would like you all to introduce you our speaker, Brad Chamberlain. He's a distinguished technologist at HP, Hewlett Packard Enterprise. Formerly, it was Cray. And so he spent like most of his time like focusing on HPC system productivity. He's the guru, yes, of the Chapel programming language. So this is what he received his PhD in computer science and engineering from the University of Washington in 2001, and his work focused on ZPL parallel array language. So now I would like to leave the floor to Brad. And Brad, thank you again for joining us online, and we look forward for your presentation about Chapel.
My pleasure, and thank you very much for hosting me. Let's see. Can you see the slides okay?
Yes.
Great. All right. Well, thanks again for hosting me. Good afternoon, KAUST. It's morning here, so you'll slowly see it get lighter and lighter behind me, perhaps as this talk goes on. As you heard, I'm going to be talking to you today about Chapel. And Chapel is all about making parallel programming much more accessible, whether you're worried about the parallel processors that are available on your desktop or laptop computer, up to the largest supercomputers, such as Shaheen. You've already heard a bit about me thanks to the nice introduction. Maybe I could just say this is a picture of what I look like when I'm a little bit more awake than I am today. I think maybe the only thing that wasn't mentioned is that I'm an affiliate professor at the University of Washington, and sometimes that can come in handy if people need somebody on their PhD committee as an external reviewer, potentially. So just wanted to mention that. One other thing I'll mention here is that I would be happy to take questions as this talk progresses, though I know that can sometimes be challenging in the distributed setting. So I also plan to leave some time at the end for questions. But if you have questions along the way, please don't hesitate to raise your hand and ask them. So let's talk a little bit about parallel computing. And this is going to be very basic. I hope it is not insulting to anyone. Parallel computing, my definition is it's basically using the processors and memories of multiple compute resources. And the idea is that by using these multiple compute resources together, we can either run a program faster than we could otherwise, or we can run larger problem sizes as maybe we could otherwise. So for example, this is a little cartoon of perhaps typical desktop computing where we have a compute node, maybe it's a laptop. It has maybe multiple processor cores and some memory. But because of the fact that most languages, or at least most of us, the way we learn to program is sequential or serial by nature, most of our programs will only run using one of those processor cores at a time. And the idea behind parallel computing is, oh, well, maybe I have 4 processor cores on my machine. If I could be using all of those, perhaps my program could go 4 times faster. And for programs that are long running, that could be very attractive. Then the other thing I could do is not just use one compute node, but use multiple compute nodes, as you would on Shaheen, for example. And then perhaps I can go 16 times faster, 100 times faster, thousands of times faster. And not only do I have more processor cores available by doing this, but I have more memory available. So maybe I can run larger problem sizes than I could otherwise. Now, we're happily living in a time where parallel computing has become very ubiquitous. So historically, like when I was a graduate student, ancient history, the only people who really had access to parallel computing were those who had access to a supercomputer like Shaheen or to a commodity cluster. Perhaps they built something themselves by connecting some Linux machines to a network or something like that. But again, happily, we're living in this golden age of parallel computing where you virtually can't buy a system anymore that doesn't have multi-core processors, which means every computer you buy is a parallel computer. In addition, GPUs are being used more and more for parallel computing nowadays. And of course, GPUs are very present due to their impact in the gaming industry. And meanwhile, beyond sort of supercomputers and commodity clusters, as you probably know, many vendors have cloud computing resources, which are supercomputer-like if you squint at them correctly. So the nice thing is parallel computing is everywhere, but one of the challenging things is that it is sort of inherently challenging to do, and we haven't made it any easier with the programming technologies that we have developed in the HPC community, I would say. And that brings us to Chapel. So what Chapel is a modern parallel programming language. By modern, I mean, think of it as kind of much more modern than C, C++, Fortran. So maybe more in the vein of a Python or a Rust or a Swift. Chapel is designed to be portable and scalable. By portable, I mean you can use it on like this Mac laptop that I'm presenting from today, and you can use it on the largest supercomputers like Shaheen, for example. It's an open source project, so we do all of our development at GitHub. And like any good open source project, it's collaborative, so we have a lot of good contributions from our users and from other developers in the community. The two main goals of Chapel are to support general parallel programming. So you should think of this as if you have some parallel algorithm in your mind and some parallel hardware you would like to run it on, you ought to be able to do that in Chapel, or we are not succeeding at this goal. And the second goal is to make parallel programming at scale far more productive. So parallelism on the desktop is not too hard. There are more and more languages that can handle that kind of parallelism. But parallelism on large-scale supercomputers like Shaheen is something that remains fairly challenging, particularly if you're not a computer scientist by training. Perhaps you're a computational scientist or applied scientist, and sort of parallel computing is new to you. And so we want to make that a much more productive, much easier experience. And that gets back to this notion of accessibility. I'm going to show really quickly just sort of an illustration comparing traditional HPC programming to Chapel. And this uses a few kind of small, fairly simple benchmarks. The first is called HPCC Stream Triad. It's just kind of a simple array computation. The second one is called RA, or Random Access, and it's all about accessing random memory all across the system. And these codes I'm showing here, very small, I don't expect you to read them, are written in C and MPI. And in the case of Stream, there's also some OpenMP. And again, these are traditional ways that people would program supercomputers today. And in fact, I would say that most large HPC applications are typically written in MPI with C, C++, or Fortran, and occasionally OpenMP. So this is sort of the de facto standard for HPC programming. Again, it's a lot of code. I don't expect you to read it. But what you can read is the Chapel equivalent. So what I'm showing in the blue here is if you took the code in these reference versions that I've shown you here, and you were to transliterate the code I'm showing you into Chapel, you'd get codes that are like this. And what you can see is not only is it much less code, but it's, I would argue, much clearer, much easier to understand. Even if you don't understand these computations or know about them, if you were to look at these, you might have some intuition as to what's going on here. And if you learn Chapel, you certainly would. And happily, not only are the codes shorter and more succinct, but they are also performing well. So these are speed up graphs. Higher is better. On the x-axis, I have the number of compute nodes, or we call them locales. So you can see I'm going up to 256 compute nodes in these graphs. And these are 36 core processors we were running on. So this is about 9,000 processor cores. In the case of Stream, you probably can't even distinguish the lines. We're basically getting the exact same performance as the reference version, and that's not surprising. Stream is fairly easy to max out. You basically, once you've saturated the memory bandwidth, you really can't do any better. In the second one, RA, we see Chapel actually outperforming the reference version in MPI. And the reason for this is that not only is the code more succinct, but it makes itself readily optimizable for the compiler and can take advantage of key features in the hardware, like in this case, support for atomic operations in the network. All right, so just to summarize this slide, the Chapel code is compact, fairly readable, and yet also delivers good performance. And that's something that we try to do across as many computations as possible. Our team is quite new to Shaheen, but my colleague Engin, who's on the call this morning, has done a few initial performance results on Shaheen, and I wanted to share them with you. These are early results. We haven't spent a lot of time looking into them or tuning them, but you can see taking that same stream program that I showed you before and running that on Shaheen up to, 2,000 compute nodes. I think this is just under 400,000 processor cores. You can see nice scaling all the way up. So, evidence that not only does it work on systems we've run on in the past, but on your system as well. So as I mentioned in my title, I'm talking here today about accessible parallel programming, and I want to throw out a possible definition of what this could mean. So imagine a programming language for parallel computing that is as readable and writable as Python. Hopefully from the code examples I've shown you so far, you might see some things that make it look kind of Pythonic in nature, even though it is not Python, but kind of similarly clear, similarly straightforward code, I would say. But where Python isn't really designed for large-scale parallel computing, it's key that Chapel be capable of that, right? So we want to have scalar code that's as fast as Fortran or C or C++, so that nothing is lost there. We want to scale up to large processor counts, as well as MPI and SHMEMDO, the two main ways that people program large-scale parallel systems today. Bilel mentioned that you'll be getting GPUs on Shaheen. We want to be as ready to program GPUs as any of the variety of ways that people are programming GPUs today, often CUDA or HIP or OpenMP. And we want to be as portable as C in the sense of there shouldn't be a question about whether Chapel runs on a given architecture. If it's a parallel architecture, we ought to run there. And then this last one sometimes makes people laugh in the HPC space, but we want to be as fun as your favorite as your favorite programming language. And the reason for this is I think a lot of us get into software and programming because we find it a fun activity. And I would say that most programmers I know in HPC, they enjoy the thrill and the results of running on a large supercomputer. Like that's very exciting to be able to run on many processors and get good performance results. But the actual programming, there aren't many people I've met who find that part fun. And I think sometimes we have a real challenge attracting and retaining people to our field for that reason. So the goal here is to make HPC programming and parallel programming fun. And this combination of reasons is why we are doing Chapel. All right, so with that, here's a quick outline for my talk today. I've just given you a little bit of argument for why we might be interested in Chapel. Next, I'm going to turn from the benchmarks I've shown you so far to a few applications of Chapel just to show you how it's been used by users in the field. Then I'll probably talk a little bit about global view versus SPMD programming, which talks a little bit about why is Chapel so much more compact than some of these traditional ways of programming HPCs. I've got a brief introduction to Chapel by example here. It's unlikely we'll have time to get to this, but I didn't want to have too little material, so I've got that if we do have time for it, and then I'll wrap up. All right, so let me dive into some applications of Chapel. On this slide, I have a number of applications that have been written in Chapel. Most of these have been written in the past 5 or 6 years, I would say. And they really vary across disciplines. So some of them are what I would call traditional HPC, modeling the physical world, like this computational fluid dynamics application here, a simulation of the universe over here in the upper right. Some of the things are more computer science problems, like branch and bound optimizations here, or some statistical analysis here. We've got some image analysis. We've got some graph computations. We've got some coordination between different hydrological models that the community studying water runoff could share using Chapel. And we've got some data science. So a great variety of different types of applications. And one of the things I like about this slide is I talked before about one of our goals being any parallel application. And this sort of shows that it's not sort of just for astronomy or just for data science, but in fact is being used across a large variety of fields. And I'll mention most of these users have given talks at our annual workshop, ChapelCon, or previously it was called CHU. So if you're interested in any of these, in many cases we could direct you to talks in which the developers of these applications are talking about their use of Chapel. I want to focus in on 3 of these applications in particular. And the reason for that is that I think they show an interesting diversity of code sizes, and types of uses of Chapel. So let's zoom in on those three. The first one I mentioned briefly already. This is a computational fluid dynamics framework. It was developed at Polytechnique Montreal. And this was done by a small group who had some existing code that they had written in C and OpenMP. They wanted to write something that was larger and more scalable. And they were thinking about doing that in C++ and MPI. And the students had heard about Chapel and convinced their advisor to let them try Chapel. He was impressed by the performance they were getting and how easily they could write the code. And as a result, they rewrote their simulator, their framework in Chapel. This is to date the largest Chapel application that's been written. It's about 100,000 lines or more. And this team is running primarily on their desktops when they're doing development, and then on HPC systems when they actually want to do a production run. This next application in the middle is a very different in code size. So where the first one is over 100,000 lines, this one's about 300 lines. And this was a case where a research group had been using Python, or no, sorry, it was MATLAB, using MATLAB to do this image analysis, and their runs were taking hours or sometimes days, depending on the size of the image. They were able to rewrite that in Chapel in about 300 lines, and suddenly were running in minutes or seconds. Not only that, they then found that an algorithm they had wanted to do, but didn't feel they had time to complete the runs in MATLAB, they could now express in Chapel and do that in a reasonable amount of time as well. This is a group that is, again, primarily using desktops, some HPC systems, and they've also been doing GPU computing for their image analysis. And then the last computation here is a statistical package that an atmospheric science group is doing. This is using the Tall Tower, what's it called? I've lost it. It's a Tall Tower Amazon Observatory, whose name I've forgotten at the moment, I apologize. And this code size is somewhere in the middle, about 5,000 lines. And this group is interesting because they are not necessarily interested in HPC programming. They're just interested in a more effective way to program parallelism on their desktop. Sometimes using GPUs, sometimes not. And so for them, Chapel has replaced things like Python, Fortran, MATLAB. And again, shows that you can get benefits from Chapel and appreciate things from it, even if you're not necessarily interested in HPC scale programming. If you're interested in these three applications in more detail, we've been recently doing a series of blog articles in which we interview users about what are they doing, why are they using Chapel, what has worked well for them, what would they like to improve. And if you're interested in reading the interviews in these cases, there's a link here at the bottom of the slides. You can find this on our blog fairly easily. And I'll be making my slides available after the fact, so you can grab these links and things like that. I wanted to call out a few quotes, though, from these interviews that I thought were compelling. For this first one, the PI of the project said, "Chapel worked as intended. The code maintenance is very much reduced, and its readability is astonishing. This enables undergraduate students to contribute to our project, something almost impossible to think of when using very complex software like ours." In the second case, Scott, who wrote this, wrote, "With the Coral Reef program, I was able to speed it up by a factor of 10,000. Some of that was algorithmic, the rewrite of the algorithm that I mentioned earlier, but Chapel had the features that allowed me to do it. And again, even though they could have expressed that rewrite of the algorithm in MATLAB, the running time would have been prohibitive." And then the third case, sorry, my window's in the way. Chapel allows me to use the available CPU and GPU power efficiently without low-level programming of data, synchronization, managing threads, etc. All right, so again, if you're interested in reading more about these experiences, this blog series is a great place to do that. One more application I want to spend a little bit of time on is Arcuda. This is a very different application than the others, and I'll explain why in a moment. So the motivation for Arcuda is, let's say you have some data science problems to solve that are bigger than you can solve on your desktop. So there's things that really require an HPC scale system to run on. Perhaps you have a bunch of Python programmers that you can apply to these problems, and you have happily HPC systems you could run them on. However, the problem is that, as I mentioned earlier, Python isn't really designed for large-scale computing and isn't particularly good at running very, very fast on these large-scale systems. So how are you going to allow these Python programmers to solve these problems on the systems you have available? That's the motivation for Arcuda. So Arcuda was the answer that was come up with by the team that was working on this. To define what it is, essentially what you have is a Python library, and you as a user are making traditional Python calls, things like NumPy and Pandas calls, and you're sitting in your Jupyter notebook perhaps doing this as you would normally do. But rather than having that execute locally on your system, what's happening with Arcuda is that all of those calls are actually implemented in a server that could be running out on the HPC, and that is written in Chapel. So you're doing something like fill this array with random numbers or sort this array or things like that. And rather than running on your laptop, those will be running out on the supercomputer where your arrays will stay resident as you're interacting with them. So the first part of the answer to the question, what is Arcuda, is that it's essentially a scalable version of NumPy and Pandas for data scientists. I'm going to show another performance graph here. This shows Arcuda argsort. If you think about data science, which for me is a lot like working in an Excel spreadsheet and doing various manipulations to the data, one of the things that happens commonly is the desire to sort the data or to run group by algorithms, which also rely on sorting. And so what we have here is some timings of Arcuda's argsort routine run up to massive scale. So the largest one here is on 8,000 some nodes. This is over 1 million processor cores. This is running on a Cray EX, so a system very much like Shaheen. And as you can see, it's scaling very nicely up to those 1 million cores. One of the nicest things about this is that this argsort routine was implemented using about 100 lines of Chapel. And it was essentially a case where the developer working on it originally just kind of Googled sort algorithms online, found a parallel algorithm he liked, and transliterated that into Chapel and had a scalable algorithm from the start. We've done additional performance optimizations since then to make better use of the network, but it still is just 100 lines of fairly straightforward Chapel. So as I said, the first answer to the question, what is Arcuda, is it's this scalable version of NumPy and Pandas for data scientists. But over time, what we realized is that this model that Arcuda presents isn't only interesting for NumPy and Pandas, but there are all sorts of other things you might want to do from Python, like maybe run FFTs or do sparse linear algebra or run on multidimensional arrays. And so what's happened over time is that Arcuda has become this general purpose framework where you can extend that Chapel server over time, add new operations and capabilities to it, and expose those to Python. And essentially kind of, anybody who wanted to do some computations in Python, but at HPC scale, can now do this in Arcuda, as long as somebody has extended the server with the right operations. And what this allows you to do is, where normally when interacting with HPC systems, we submit a job and then maybe go have lunch and then come back and see if our job is completed and what the results were. Arcuda presents a way in which sort of interactively you're sitting there trying something, running it on the system, seeing what the results are, adapting to that, running something else. And that interactive mode is something that I think is refreshingly unique in the HPC space that Arcuda enables. If you're interested in learning more about Arcuda, it has a website that gives sort of an explanation similar to what I've just done here. It is developed as open source as well, and so I've got a pointer here to its GitHub repository. And we've recently published another interview in our series with one of the original developers of Arcuda, Bill Roos. And so if you'd like to read more about why he's chose Arcuda, you can see this series for that. There's this great quote from him where he says, "I was on the verge of resigning myself to learning MPI when I first encountered Chapel. After writing my first Chapel program, I knew I'd found something much more appealing. Chapel's separation of concerns immediately felt like the most natural way to think about large-scale computing. I would highly encourage anyone wanting to get into HPC programming to start with Chapel." All right. So next, I'm going to talk to you a little bit about global view versus SPMD programming. These terms may not mean anything to you, but I'm just about to define them for you. So going back to this slide earlier, I think a lot of people look at this and say, well, what accounts for the huge amount of difference in code and the complexity of the code between the reference versions and the Chapel versions? Like, how can Chapel be so compact? And there are a few answers to this. One of them is simply that Chapel is a more modern language than C. And so we've learned a lot of lessons from other modern languages, particularly scripting languages, and applied those to the HPC space. And that accounts for some of the compactness here. Another element is that we have built-in notions of parallelism, whereas most traditional languages have not done that, and so it's been tacked on later, and that allows things to be more compact as well. But I think the bigger issue is this question of global view programming versus SPMD programming. And so again, let me define what that is. So if I have a problem for you that I want you to solve, say you've got a one-dimensional array, and I want you to replace each of those array elements with the average of its neighbors. In scientific computing, we'd call this a three-point stencil because we're sort of looking at 3 points, the element we're computing and the two elements around it. So when I say that to you, I hope that the picture you have in your mind is something like this. So in these arrays, I'm going to take these dark purple elements, and I'm going to assign them the average of the left-shifted orange elements and the right-shifted orange elements, add those together, divide by 2, and assign to these middle elements. And if that's the picture you have in mind, that's what I would call the global view, because you're thinking about the problem as a whole and what the computation needs to do. So in HPC programming, most of our programming models are what we call SPMD, which stands for single program, multiple data. And the idea there is that you are writing a single program, but then you're running it on multiple nodes or multiple processes. And so the way you write that program is very different. And so for this averaging computation, if we were to write this in an SPMD model, again, we would have our arrays with 6 elements each in my little cartoon here. But if I were running on 3 compute nodes, I would divide those vectors into 3 chunks. So each compute node would have 2 of the 6 elements. And because I'm doing this averaging step, this stencil operation, what we often do is allocate some extra elements so that we can get the elements that we don't own that we're going to need to do our computation. So for example, to compute this purple node here, I'm going to need this orange node over here owned by my neighbor in addition to the one that I own here locally. So the first thing we often have to do in these computations is do some communication. So taking those orange elements that we're going to need to read, we're going to communicate copies of those to our neighbors so that they now have all of the data that they're going to need to do this computation. And then once we've done that the communication, we can actually do the computation. But again, rather than describing it as a whole, each processor is only focusing on its local data and doing the averaging step using the local elements that it owns. Okay, now this is something that I think you could all do. It's easy to understand conceptually what's going on here, but it results in a lot more details in the code. And I'll show you that in just a second here. So if we look at the Chapel code for this computation, the code here is what we call global view. So I've got my main procedure. I declare a problem size n. I declare a domain, which is an index set using that problem size of n. And then I can do things like this. Oh, I forgot to declare my arrays here. That's funny. I must have broken that in my slide at some point. I apologize. There should be a line here that declares my arrays A and B over this domain D. I don't know when that disappeared. But then when I do the computation itself, I can say, for all elements I in the inner portion of this index set, B sub I equals A sub I minus 1 plus A sub I plus 1 divided by 2. So again, even though you don't know Chapel, hopefully, other than the fact that I forgot the arrays, this is a fairly straightforward expression of the computation, just what you'd expect, sort of, let's assign the elements the average of their 2 nearest neighbors. So let's look at what the, oh, sorry, before I go on. So our model here for Chapel is that conceptually, at the beginning of time, a single task is running main, and then when we hit parallel constructs in language like this for all loop, we are creating new threads and tasks, potentially across multiple compute nodes. And then when that loop ends, we are collapsing back down to a single task. So again, part of the notion of the global view is that we're describing the computation as a whole, including all of the parallelism using concepts in the language. All right, now let's look at the single program, multiple data version of this. This is pseudocode. I've written it using a Chapel syntax. And this uses concepts similar to what you'd see in MPI, though it's not literally MPI. So as I mentioned, in the single program multiple data model, you're writing a single program, but you're running multiple copies of it. So where in the Chapel code, only a single task is running main, in this SPMD model, you have many, many copies of main, 1 per processor or 1 per core potentially, and each of them is running their own copy of main. So you can see things like where I take my problem size n as before, I have to compute like, well, how many of the values of n do I own? That's sort of n divided by p, the number of processors that are running this code. And when I declare my arrays, I'm declaring them just over my local chunk of the data, not the whole data. So as we execute this code, all the copies of the program are going to be executing it. They may take different branches through the conditional where we're dealing with boundary conditions, but we're all running all of the code. And when we get down to this loop at the end, we're all running it over our local chunk of the data. So again, something that probably you could all write, but as you can see, there are a lot more details to take care of. And I've even done some simplifying assumptions here, like assuming that my problem size n divides by p evenly. If it didn't, and often it doesn't in real life, I would have to do additional things to kind of fix that up and have some processor zones slightly more data, some slightly less. All right, so this is sort of the distinction between the global view that Chapel provides and the SPMD view that MPI and frankly most other parallel programming models for HPC provide. And this is the main reason I would say for why reference versions or sort of traditional ways of programming HPC are so verbose and so complex, and Chapel versions are so much more compact. And again, a secondary factor here is C. C is a little bit of an old-fashioned language at this point. It requires you to do a lot of things manually. Chapel is a more modern language, lets you do more things in a more automated way. All right. One thing I want to say before wrapping up is that because we're a general purpose language, even though you don't have to write code in an SPMD manner, sometimes SPMD is the best way to write a computation. In fact, that arg sort I was showing in Arcuda earlier is an SPMD computation. And so because we're general purpose, you can still write SPMD computations in Chapel. This is sort of a small sketch of what that might look like. So we haven't taken anything away from you. Hopefully we've just made your life easier in many cases where this is not required or the most natural way to do it. All right. Next, what I was potentially going to do was give you a little bit more of an introduction to some of Chapel's features. As I mentioned earlier, I didn't think I would actually have time to get to this. And in fact, looking at the clock, I don't, because I'd like to leave some good time for questions here. So I'm going to jump ahead instead to my wrap-up. But we can come back to these slides perhaps in a future seminar if people are interested in getting into a bit more detail about how Chapel works. So wrapping up. Just to summarize, I believe strongly that Chapel is unique among programming languages. Unlike most languages, it has built-in features for scalable parallel computing, and this makes it ready for HPC scale computation. And I'm not aware of another language that is as HPC ready as Chapel is. It ports and scales from laptops to supercomputers. We heard that from some of our user testimonial earlier. Most of our users do most of their development and debugging on their laptops, and then once they have a code that is working correctly, they can take it, recompile it for the supercomputer, and have it work there immediately. As I've shown you a little bit today, Chapel supports very clean, concise code relative to conventional ways of programming supercomputers. And something we didn't really talk about today, although I think I mentioned it, is that Chapel supports the ability to program GPUs as well as CPUs, and to do so in a vendor-neutral manner. So it doesn't really matter whether you have NVIDIA GPUs or AMD GPUs, your same Chapel code will run on both of those without problems. As I've shown you a little bit today, Chapel is being used for productive parallel computing at scale. Our users are reaping its benefits using very practical applications that are doing cutting-edge science in a variety of fields. As you've seen, it's applicable to domains that are as diverse as physical simulations of the universe, climate science in the case of that image analysis, and data science in the case of Arcuda. And I think Arcuda is a particularly unique example of an application written in Chapel because of the fact that it gives you this interactive ability to drive an HPC system from Python and from a Jupyter notebook. Again, something that is not how we typically interact with HPCs. There are many, many things that I couldn't get to today that are worthy of more time. You've only seen a little tiny bit of Chapel, and I haven't really had time to even teach you very much of it. So that's something that requires more time, obviously. I've mentioned the GPU support, but we haven't really seen how that works. We've got some nice tools for Chapel. So if you're a VS Code developer, and I know more and more people are, we have good VS Code support and an integrated linter, which makes developing Chapel in VS Code, I think, one of the best ways to do it today. Arcuda, though it's kind of just one of our many applications, the fact that it is this general purpose framework and provides this interactive experience makes it fairly unique. And I think, therefore, it's an application that could definitely get more of a discussion than I was able to give it today. We're quite new to Shaheen and have only run a few benchmarks on it at scale. but that is something that we're interested in doing more of and talking to you more about over time if you're interested in that. And for those of you who might be interested in compilers and how compilers work, we have a number of optimizations that are interesting that I haven't been able to talk about today as well, and many, many other things as well. So, as I wrap up, I just wanted to say that our team would be happy to follow up on any of these topics or others that you may have in mind as our schedules and your interest permit. I've been able to talk to you this morning, and again, I appreciate the invitation to do so. I just want to call out that this work that I've shown you is the work of a large team. This is our team called the Advanced Programming Team at HPE, and I just want to give credit to the other members of my team who helped us get here today. If you'd like to engage with our community, we have a number of live, although everything today is virtual it seems, events. We have an annual workshop called ChapelCon. That's a multi-day workshop with tutorials and presentations that we encourage you to attend. That'll be in October this year. Our weekly project meetings have been going on for years, but we've recently opened those up to the community. Those are on Tuesdays. If you'd like to join us, we'd be happy to have you attend those and listen in on how we develop Chapel. We have a monthly demo session where we show something off about Chapel, and we record those, so those are available on YouTube for past ones that have occurred. We have a number of ways we talk to the community electronically, broadcasting things to them. We have a blog that is published about bi-weekly on average. We have a quarterly community newsletter that's a roundup of Chapel activities, and we do announcement emails about big events like ChapelCon. If you have questions or want to interact with us, we interact with our users and community in a number of forums such as Discord, Reddit, Gitter, GitHub issues, email. So reach out to us by any of those. And for those of you who are social media users, we have accounts on most of the major platforms, and that's a good way to follow the project and pay attention to what's been going on lately. Our Chapel website has a bunch of information about the language and also has links to all of these different things that I've just mentioned. Again, I'll also make these slides available offline. And I'll just put my summary up again and open it up to questions if there are any. Thanks again for hosting me, and it's been a pleasure to have the opportunity to speak to you today.